You may recall that in a previous thought primer, we discussed this idea of statements making sense. And I explained in one of the lectures in that thought primer that in our ordinary casual conversations with one another, we might ask somebody something like, does that make sense? And oftentimes what we're really communicating or asking is, do you understand what I'm saying? Or is what I'm saying understandable? We might respond to what somebody tells us by saying, oh yeah, that makes sense. And what we're oftentimes really communicating is, I agree with you. But strictly logically speaking, for statements to make sense, they have to be statements that can be true. And if we have a group of statements, more than one statement, they can make sense together if they can all be true at the same time. And a strategy that we worked on to be able to compare statements with one another was ordinary truth tables. We developed ordinary truth tables for the statements we were considering in order to evaluate their truth values at given moments in time. And what we were looking for is it possible for these statements to be true at the same time? In other words, is there any shared line on their truth tables where both of the statements are true? If there are lines where they're both true, then those statements are consistent. It's possible for them to both be true at the same time. They make sense. On the other hand, if we develop truth tables for some statements and we see that on no lines are they sharing a value of true, then we say these statements are inconsistent. It's not possible for them to be true at the same time. They don't make sense together. Okay? Now we can take a couple of statements, simple statements like Jerry likes chocolate and Nihal likes vanilla, and we can use our operators to create compound statements out of these. So we have here G wedge N, which means something like either Jerry likes chocolate or Nihal likes vanilla, or Jerry likes chocolate unless Nihal likes vanilla. And we have this other statement over here, tilde G dot N. This says something along the lines of Jerry doesn't like chocolate and Nihal likes vanilla, or it's not the case that Jerry likes chocolate and Nihal likes vanilla. Now we could compare these two statements to see if they're consistent. Is it possible for them to both be true at the same time? Or inconsistent? Is it impossible for them to both be true at the same time? By developing ordinary truth tables. But who wants to create all those lines when we could use indirect truth tables for statements, okay? So we're going to focus in this thought primer on how to create indirect truth tables in order to determine if a group of statements are consistent or inconsistent, okay? And we're going to develop indirect truth tables for statements very similarly to how we use truth tables to evaluate arguments for validity. We're going to write out our statements on a single line, and we're going to separate all of the statements that we're considering with a single line, not a double line, okay? And then when we develop indirect truth tables for arguments, we work from the assumption that the conclusion is false and all the premises are true. That's because when we're evaluating arguments, we want to know, is it possible for the conclusion to be false when all the premises are true? But when we're evaluating statements for consistency, what we want to know is it possible for all of these statements to be true at the same time? So we're going to assume that all of the statements we're evaluating with an indirect truth table are true statements. So we're going to begin by marking all of the main operators of our statements with a value of true, and then we're going to deduce all of the logically necessary values to see if we can completely deduce the values of the statements we're considering without running into a contradiction. So here we have two statements, G wedge N and tilde G dot N, and I can't logically deduce any truth values out of G wedge N because, as the truth table shows, there's three possible true-false combinations under which the wedge can be true. So I can't know the value of G or N just knowing that the wedge is true, but I do know that with dot, there's only one way a dot is true, and that's when both sides of the dot are true. So N has to be true and tilde has to be true. And if N's true here, N's true there. And if tilde G is true, G is false. And if it's false there, it's false there. And I've not run into any contradictions. I've completely determined all the logically necessary truth values, no contradictions, and that proves these statements are consistent. Okay, now consider these statements, g dot n and tilde g wedge tilde n. Again, I begin by laying out my sentences, my statements that I'm evaluating on a single line, separating each statement with that single slash, and then I work from the assumption that the main operators of all of my statements are true, and then I just deduce the logically necessary values with that assumption in mind. So I know from my rule of conjunction or dots that in order for that dot to be true, both G and N have to be true. Well, G and N are true here, and this line represents one moment in time. G and N have got to be true there. And if G and N are true there, then tilde G has to be false. And tilde N has to be false. And it's the tilde operators that determine whether or not this wedge is true or false. And we have a contradiction, because the rule of disjunction says that for the wedge to actually be true, at least one side of the wedge has to be true. And in this case, both sides of the wedge are false. And this gives us an indication that these statements are inconsistent. It's not possible for them to both be true at the same time. They don't make sense.